Hi, this is Stephen Brower from Raton Valley Community College, and this is the exciting conclusion to recursion in our data structures course. Part 1 had an intro to recursion and showed the factorial. Part 2 showed recursion on an array, and this Part 3 will look at recursion on a linked list. Previously, we had an iterative method, the exist method, that was inside singly linked list that would check to see if, well, something did exist. And it would start off by cursor being established with head, and then cursor would be advancing going through the list, and then stopping either once it found it or if it fell off the end of the list. So that was an iterative approach for doing exists on a singly linked list. In a recursive part, well, the recursive part would actually be on a node itself. And so if we look at an individual node, we basically say, well, am I the value we're looking for? And if we're the value we're looking for, a grade will return it. If not, it'll then say, okay, well, let me ask the node after me to see if it has the value that we're looking for. So in other words, asking the node after it if it has the value before. Well, to initiate this whole process, we need to begin with the first node in the list. Well, head is not available outside of our singly linked list. We're not returning it back to whatever program is using our singly linked list. And so we need to sort of initiate this process. So the exists method that would be inside singly linked list would be looking just in terms of head. So if head is null, well, it can't exist because the list is empty. So if head is null, it'll just return false. Otherwise, so from the list point of view, otherwise it'll turn to head and say, look at your node. Basically, I'm telling to look at this node and see, does the value exist in it itself? So this is going to initiate the process. So this method right here, this is not a recursive method here. This is going to call the recursive method that's inside of node. So now inside of node, so up to this point, all we had was get data, get next, set next, and when we had doubly linked lists, set previous, get previous, and the constructor. This would now be taking the logic for exists and moving it down into the node. And I used the term about initially our linked list not being self-aware. Well, we are now making the list aware that there's a list beyond it. So when this is running in the context of a node. And so initially, remember here, we're triggering it starting from head. And so initially, it's on this node right here is where this method will run. So we're passing into the method that's for this node, we're passing in a value. And so what it'll do is it'll compare its data to see if it's the same as the value. If it is, it'll return true. And then that this right here alone becomes a base case because it's not calling itself. So if we found what we're looking for, we're done, and we're going to pass true to whatever had called us. If the data is not the target, it'll check to see, is there a next? And if there's not a next, so if there's nothing after it, then it would return false. Also another another base case. But if it isn't false, like it is in this case, if it isn't null, like it is in this case, then we'll say as far as this node here, so this head node, what it will do is it would return, well, it's going to ask the node after it, well, does it exist there? And so then control kind of then goes over to this node. So now exists is running on this node. The data that's referring to here is this node's data, and it will be comparing, does this data equal the target of what we're looking for? If not, it'll look at this next to see, is it null? And if it's not null, then it'll turn to the node after it and say, well, does the target exist in your list? And so on this call right here, next exists target, then that is, from this perspective, saying, let's go to this next one here and find out, does the exists here? So in terms of doing a reduction in the list, the fact that we're advancing to the next node, we're advancing to a smaller list. So the list is going to keep getting smaller in terms of the list that we're dealing with. So we're doing a reduction in terms of the list because eventually we're going to get to the very end. So when we finally do get to this node here, it'll say, well, does the data exist? And let's say it doesn't. And is next null? Well, next is null. So in that case, it'll just return false. So if we get all the way to the end here and haven't found the value that we're searching for, this is going to return false to here, which this is returning false to here, which this is returning false to here, which this is returning false to the singly linked list. If we had, if we had begun this process on this list, and suppose we were searching for 10. So suppose we asked, does 10 exists? So we're calling the exist method, passing it the value 10. And so here, if head is null, well, it isn't null. So it's going to say, okay, let's talk to this node. And so, okay, you node here, see, does 10 exist in this node? So then the exists method here is running on this node and say, well, does data 8 equal the target 10? No, it doesn't. So is the next null? Well, it's not null. So what we're going to do is we're going to return whatever this node says that it finds. So we're going to the next node, and exists is now going to run here. So when the exists runs, so we're receiving the 10, it's going to compare, does data, which is 6, equal the target? It doesn't. Is the next null? The X is not null. So now we're going to say, okay, this node is going to return what the following one does. So from the next node here, now exists is going to be running on this node. 10 is the value that we're looking for. So I ask the question, does data equal target? It does, because we found the 10 that we're, before I get interrupted, I do apologize. We were on this node here, and we just asked the question, does data, which is 10, equals the target, which was 10, and it does. So this node is going to be returning true, and it's returning true to this node where it was doing a return to this node, which this was doing a return to the list itself. And so the true is being propagated up, and then the true is what is returned. So doing recursion on a data structure, so looking at these two methods here, these two methods here, this is in the singly linked list, and this just calls exists from the first node head. Exists is now in the node, so the logic is in the node, so that means each node actually has the exist method, but we're initially beginning by calling head and seeing does it exist there. Here are our base cases. These two base cases right here. If we found what we're looking for, great, we return true. If there's nothing after us, we return false. Otherwise, we'll return what the next node is passing to us. And so then it goes to the next node and repeats that process. So this is the recursive call. And the reason why we're saying it's reducing is that because we're calling it on next, we're dealing with a smaller list. And when this one calls it on next, we're dealing with a smaller list. And since we keep doing next, we eventually get down to the last node, or we fall off, or there is nothing after the node that we're on. So this is a simple way of doing the exists. Now let me talk to a more complicated way. Well, one, I did this as an unordered list. Suppose we had an ordered list. If we had an ordered list, if we got to the point here where if the data was not the target, then we could then check to see, well, is the data or is the target before or after data? And if the target is before the data, that means everything after is greater, and we don't have to actually go any further. So this part right here should only occur is if the target is greater than data. So it would make this a little more complex, but at least it would prevent it from having to march through the whole list if it was in order. So some other recursions that can be done, remember count occurrences. So count occurrences, we actually could basically say whether or not the node we're on, does it count? And then it would go to the next node and say, well, how many counts do you have? And keep going to the next node, how many counts do you have? And that can propagate up as well. What I will just allude to is that add and remove can also be done recursively in a linked list. They're a little more involved, a little more complex, but those could be written recursively as well on a linked list. And it would be a similar format where the initiating of it would occur from the list itself. It would turn to that first node and then do whatever the action is based on that first node. That's enough for now. This is a foreshadow for what we're going to be doing next week when we deal with trees. And part of the reason is there are some algorithms that are easier to do recursively on trees than it is to do them iteratively. So the reason why recursion is done here is to get us familiar with it before moving on to the next topic. That was a train wreck. That's good enough.